Hello everyone. So myself Rudra Narayan, and today we are going to discuss a very important topic, which is first order reaction from chemical kinetics chapter. So let us consider what is first order reaction. So first of all, we all know what is order of reaction, which is the sum of the powers of the rate law. So rate law would be written like this: R is equal to rate constant K into two different reactants. Let us consider their A and B, and we have some power there, X and Y. So order of reaction can be defined as X plus Y is the sum of the powers of the concentration in the integrated rate law equation. So this is valid for elementary reaction. Okay, for elementary reaction we just can add up the coefficient there, and if we know the rate law, then we can easily calculate the order of reaction as X plus Y. So let us consider what is a first order reaction first. So let me write a rate law equation for a first order reaction, which will be, let us consider an imaginary reactant which is A is converted to a product which is B. Then a first order rate law equation or integrated rate equation for this, a first law rate law equation will be R is equal to rate constant K into A to the power 1. Okay, where A is integrated inside a square bracket, and which means the concentration of the reactant A. So as we know, coming to the concentration, when time is T is equal to 0, means reaction hasn't been started yet, then we can say we have full amount of A, which I am taking as small a, or full concentration of A, which I am taking as small a, and B, the product will be 0 because reaction hasn't been started yet. Then at time T is equal to T1 or Ty or Tz, we can say X amount of A has been decomposed to product B, or X amount of A has been converted to product B. So the amount of A will be A minus X, and the amount of product will be X. Okay, so after that we can say, as we know from here, that a rate is equal to minus dA by dt, which is equal to plus dB by dt is equal to Ka to the power 1. What is dA by dt? Why it is minus? So we are considering rate as the negative sign of the differentiate of concentration of A and positive differentiate of concentration of B. Why negative sign comes here? Now the reactant is decreasing. And positive comes here because the product is increasing in amount. So we consider rate as this. And coming into the derivation of the integrated rate equation, from this rate law we can say that minus dA by dt is equal to Ka to the power 1, where we can take like this: minus dA by A is equal to K dt. On integrating both sides, what we will get? We'll get, so as of now we consider that we know all the basic integrations. So here we will get, negative sign will come out and this will be ln A, and here we will get K T, because integration of dt will be T, and here integration of dA by A will be ln A, and then we will write plus C, which is integrating constant, So up to this it is understandable. Then we have to calculate the value of integrating constant, which will be our, let us consider T is equal to 0, This is equation 1. And when we consider t is equal to 0 in equation 1, we will get minus ln A naught. Ln A naught is the concentration of A at initial concentration of A, and we will put Kt is equal to 0 plus C. So we will get the value of C as ln A naught or minus ln A naught. Okay, so this we can say as equation 2. After that, we have to calculate the rate equation in a different format, so we can put the value of C here in equation 1. So let me erase all these things. So when we put the value of C, which is ln A naught minus ln A naught, so here already minus ln A is equal to Kt plus ln A naught. Okay, so plus minus ln A naught. But we can say now that this minus ln A naught will come onto this side, and this will be minus ln A plus ln A naught is equal to Kt. Or what we know, that ln A plus ln B or ln A minus ln B will be divided. So how we can say that? That it will be ln A naught divided by ln A. And if it is plus, then we can say it is multiplied when it goes inside the logarithm bracket. And this will be Kt. So this we can say as our equation 3. And which is the integrated rate law equation for a first order reaction. So coming to what we can do from here, that we can say we can convert this ln into log, and the ln is 2.303 log A naught by A, which is equal to Kt. Or what we can do, if we have to calculate T, then we can take K here. If we have to calculate K, we can take T here. Okay, let's come into the graphs. So let me erase all this. From here we can erase, and we need two equations. So first I have to take this equation. So from here what we can say, that log A naught by A, don't forget to put the square bracket signs, which is the concentration sign, and we can say that it is equal to K by 2.303 T. So let me compare this with the equation of straight line. Y is equal to mx plus c. So here c is equal to 0 and y is equal to this, which is log A naught by A, and m is equal to the slope is equal to k divided by 2.303, which is positive. So if the slope positive, the graph will go downward or upward. It will go upward definitely. So let us consider, so this will be on y axis, log A naught divided by A, and this will be on x axis time. So let us consider slope is positive with 0 intercept, so we have to take it from the origin, and here slope m is equal to plus k by 2.303. So up to this we got the rate law equation and the graph for the first order reaction. So let us consider when we take two different first order reaction, or we can take the first order reaction for first order equation for two different time periods. So let us consider at time t1 and t2. So the first order equation at time t1 will be kt1 is equal to 2.303 log A naught by AT1, where KT2 is equal to 2.303 log A naught by A T2. So let us consider this as equation 1 and this as equation 2. So what can we do? Then let us divide equation 1 and equation 2. Equation 1 divided by equation 2. So it will be T1 divided by T2 is equal to log A naught divided by AT1 whole divided by log A naught A T2. So what will happen then? Then we can do this like this will come up and get multiplied here, and A naught will be cancelled, and we will get T1 by T2 is equal to log AT1 divided AT2 divided by AT1, which is another important result, and we can use this in different type of question to calculate T1 and T2. Okay, let us consider the half-life period. How to calculate the half-life period? So we have the rate. So let us consider how to calculate the half-life. So half-life means half of the reactant. Half-life means half of the reactant is consumed. Half of the reactant is consumed. So let us again consider that hypothetical reaction where A is converted to product B. So at time T is equal to 0, it was A, and at time T is equal to T half, it was A minus A by 2, because half of the reactant, initial amount of reactant is consumed, and this will be A by 2. So let us consider the rate equation again, which is equal to KT into 2.303 log A naught, which is the initial concentration of reactant, divided by A T half, which is the half-life concentration of the reactant, which is equal to again A by 2, because A minus A by 2 is resulting in A by 2 only. So let us calculate the T half. T half is equal to 2.303 divided by K into, here we can put A by 2. So this will be cancelled and 2 will go off. So it will look as log 2. So let us write again 2.303 K into log 2. And we all know the value of log 2. So what will be the value of log 2? Log 2 is equal to 0.3010. Okay, so let us put it there. T half is equal to 2.303 into 0.3010 divided by K, which is equal to 0.693 divided by K. So this is the half-life period. So what graph we can plot? We can plot T half versus initial concentration of the reactant. So we can put T half versus initial concentration. So as of here, you can see any like A naught value. So T half doesn't depend on A naught. So A naught value will not be differed as the T half value increased or decreased. So here T half is independent of initial concentration A naught, initial concentration of reactant A naught. So to this much we can discuss in the first order reaction and its half-life period.